Hello, ladies and gentlemen. Yes, I'm Vitaly Kamluk, and I'm going to help you embark on your first dive into IoT research. But before I start, yes, many of you know that I usually present using some non-conventional tools and means to deliver non-conventional content. And I wanted to keep the level. So my surprise to you is today you probably expect something similar. Yes, I used PowerPoint to create PowerPoint slides for the first time in my Pecha Kucha experience. So let's go. IoT research. Why are we doing this? Well, first of all, reason number one, there is estimated 30 to 50 billion devices connected from the IoT world to our internet. So it's also our research objective as Kaspersky research team, and Eugene also emphasized that this is the future, IoT research. And new experience for me, security flaws, privacy violations, and so on. So how did I do this? I want to share with you. First, I bought a device, something that is more or less popular, recent product, inexpensive, so it can be replaced in case it fails or burns. And this is what I had, a device with Wi-Fi, Bluetooth, app-controlled camera that I decided to analyze. So what are the possibilities to analyze? And first of all, the objective of our research is to get to the firmware so that it becomes from the hardware domain, goes to the software problem. Possibilities, intercept the update process, have remote access, or dump the flash memory chip and then analyze its contents. So we'll go through methods one by one. Method number one was to intercept the update process. And but for this, you need a complicated infrastructure set up so that you can control all the Wi-Fi links between the smartphone and the camera, between the camera and the router, and so on and so forth. It is complicated, yes. Is it fruitful? Well, you'll see in a minute. First, what I learned is that, well, there is some network traffic. Most of it is encrypted, SSL protected. Although you can do man-in-the-middle attacks and you can even intercept upgrade process, the firmware you get is encrypted. So you can't really get to the firmware files just by intercepting the communication. Luckily, I kept researching and I found previous non-encrypted firmware just by intercepting the URLs where it was downloaded from. You can do through the web search of Aristotle, and as a result, you can get a set of older firmwares that are not encrypted. However, of course, you want to analyze the firmware that is actually running on the device that you have in hands. So one of the recipes I learned from the community around this research is you can actually downgrade the firmware, and then it will run probably this unencrypted firmware you managed to find. In my case, there was no luck because the device wouldn't even accept the older firmware because the hardware profile of the device did not match. So I went for method two. Try to poke with remote access and API and expose services through by scanning the ports of the device or the Wi-Fi and trying to find like default credentials or anything that can get me onto the device, get a shell so that I can play with this device. However, it's long and very unreliable method. It's kind of dealing with a black box. So I went for method three, actually physically disassembling the device. And it's the first time experience for me because I'm a software guy. So I had to, pull off the things and then look into the printed circuit board, the PCB, and try to analyze how it is built, how it actually operates, what we can extract and what we can learn from by just observing it. So I took a magnifying lens and started looking into the different chips and different components soldered to it. Well, I could identify some of them by just looking at the labels on them, by the part numbers and so on. Your goal is to find the memory chip where the firmware is actually stored. So keep looking until you find one. In my case, there was a hidden chip that was hidden behind the lens. So you have to disassemble the lens, exposing the sensor matrix, and if you scratch that, you spoil the whole camera. But yeah, you have to carefully detach it, and then you can see the chip in front of you. The label on top of it will tell you that this is a memory chip. In my case, it was 8 megabyte memory flash chip. That was basically the target, the objective I was looking for. That contains the firmware in, of course, non-encrypted form, because this is how it must boot and operate eventually. So then your target is to dump the memory of this chip. How do you do that? I used a soldering station, so I just bought different components, very cheap. But the most reliable way is to use a heat gun instead of the iron. Because the component is very small, as you can see here, and you need to be very precise not to break any pins or any contacts and not to spoil the PCB. Once you get that, what do you do with the chip? If you unsolder that, then you need a SPI flash dumper device. In this case, I used a device called Tigard from Joe Fitzpatrick, a big fan of SAS conference, by the way, presented previously, and this special clip for the SPI memory chips. I clipped that, connected to the Tigard, connected to my PC through the USB-C, and I could dump the contents of the chip. With this command, it runs on all platforms, Linux, Windows, and Mac. You can get the device, the dump of the chip, and then analyze the contents and the structure of the firmware file. This is already a good start. We have the actual code running. You can look for vulnerabilities and so on. But the best is we want to have live presence, the shell on the actual camera. How do we do that? We need to find something called UART interface, a way to control and see what's going on, what device is printing, and a way to interact through the keyboard with the device. You need to identify the pins that are unlabeled in my case. You have to deduce the logic based on multimeter response, and this is how you can identify the purpose of the pins. Then you connect through the same Tigard device, which is a multi-purpose device, and you can attach it to your computer through USB-C again, and you can see the output of the serial console. Through this console, you can see that there's a U-boot bootloader used to start Linux kernel. So this is what most of the IoT devices are running, a kind of minimal, quite old Linux kernel. And then eventually it goes to the press enter to activate the console. So you can have interactive shell on the device just by wiring it to a computer. Then, of course, the last question is how to get the root shell, because you don't have the credentials to enter. You don't have login and password. So with this little bit of trickery and magic that you do with the bootloader, the U-boot, you can modify the command line for starting loading the Linux kernel, and then eventually change the root password and log in with the root credentials that you define. So what is next? My final slide. You can enable SSH or Telnet for convenience. You can analyze binaries and API. You can intercept or man in the middle traffic by replacing root certificates. You can have native debugger on MIPS CPU that it is running, and you can focus on the main part, privacy and security analysis of IoT. Let's all do this, so don't be afraid of this journey. Thank you very much.